the parallel moment of the parallel axis theorem for an area, or we call that one as the transfer formula for moment of inertia. So let us try to consider this the x-axis, and this is now the y-axis. So we have now this body. Now considering now that the centroid of the body is located at this point. So that is therefore the centroid of the body. So let us try to consider that this is therefore the axis located in the centroid of the body, and let us consider this one as the x prime axis, and this one in here is now the y prime axis. So we now have your y prime axis. Now again, let us try to consider a differential area of this of the given total area. Now such that if you try to consider this one as the differential area, which is now having a differential area dA. Now the distance of this differential area from the centroid of the total area, is y prime. So this is now your y prime. And the distance of this differential area from y prime is now known as, or that is now your x prime. This is your x prime. Now, the distance of the centroid of this area from the x-axis is equal to d sub y. So I'm just going to call this one in here as the distance d parallel to the y-axis. And the distance of the centroid of this area from the y-axis, let us try to consider this one as d, the distance parallel to the x-axis. And this is now your dx. So that the distance of the centroid of this area from pole O, that is now equal to d. So that one is now equal to d. So that the moment of this differential area about the x-axis is now equal to, so we have to take the second moment of the area about the x-axis. So we have your dix is now equal to the integral of y prime plus dy. So that is the distance of the differential area from the x-axis. That is y prime plus the distance from the centroid of the total area to the x-axis, which is parallel to the y-axis, square multiply this one by dA. And this is therefore equal to, so we now have the integral y prime plus dy quantity square is equal to y prime square plus 2y prime. We now have dy plus the distance parallel to the y-axis, dy square multiply this one by dA. So you're integrating both sides. So we now have your ix is now equal to the integral. So your yx is now equal to the integral, okay, to the integral of y prime square multiply this one by dA plus the integral of 2y prime. So we now have 2 the integral of y prime multiply this one by the distance parallel to the y-axis, and then plus the integral of dy square multiply this one by dA. So the integral of 2 dy square, we have so let us try to write this one. Ix is now equal to the integral of y prime square multiply this one by dA plus we have 2, we now have your 2, we have your d, and that is now your y. So that is the distance. dy in here is the distance from the centroid to the x-axis. The integral of d at the integral of y prime multiply this one by dA plus, okay, dy square in here, your dy in here is constant. So we can place this outside the integral sign. So we have your dy square multiply this one by the integral of dA. So that we now have your Ix in here is now equal to the integral of y prime, the integral of y prime square dA is now equal to the moment of inertia about the x prime axis. So that is the moment of inertia about the x prime axis, or in other words, that is the moment of inertia of this figure about this area with respect to the centroidal axis. Now, the integral of y prime dA is equal to bar y. So you try to take note, the integral of y prime dA is equal to, we now have your bar y multiply this one by a. Since your x-axis coincides with the centroid of the total area, hence your bar y in here is equal to 0, and that one is equal to 0. Plus, we now have the integral of dA is now equal to the area, multiply this one by d square. So this is d parallel to the y-axis. Or your Iy, also, you will going to get your Iy is now equal to I y prime plus a, we now have your d square. So your d in there is the distance parallel to the x-axis. Hence, the polar moment of inertia is now equal to, again, your y prime is the moment of inertia with respect to the y prime axis, which coincides with the centroid of this body. So, your IO is therefore equal to the moment of inertia about the centroid of this area, plus A multiply this one by this time, this is now the moment arm, d square. Multiply this one by d square. Now, So let's try to get now the radius of gyration. Radius of gyration, and this is denoted as K. Now, I will now going to consider this one in here. So if we have an area, so this is your area. So let's try to get now the radius of gyration. So again, this is now the x-axis, and this one is now the y-axis. Now, if this area, total area, is squeezed in the direction of the x-axis, so that area is squeezed in the direction of the x-axis, so this is now the area, total area squeezed in the direction of the x-axis. So this is therefore the area. So we now have the total area in here is A. So that the distance of this squeezed area from the x-axis is known as your kx. So this is therefore known as your kx. So this is the radius of gyration with respect to the x-axis. So from the definition of the moment of inertia, the moment of inertia with respect to the x-axis is now equal to the total area, multiply this one by the moment arm, which is kx squared. That is equal to kx squared. And your kx, or the radius of gyration with respect to the x-axis, is now equal to the square root of the moment of inertia about the x-axis all over the total area of the body, all over the total area. Now, again, if the body, let's consider, this is now the y-axis, and we now have the x-axis. So this is your x-axis, that is now your y-axis. Now, again, if the area again is squeezed in the direction of the y-axis, so this is therefore the area which is squeezed in the direction of the y-axis. So we have the total area, and the distance of this squeezed area to the y-axis is now your ky. And ky in here is now the radius of gyration with respect to the y-axis. Okay, so again, from the moment of inertia with respect to the y-axis is now equal to the total area, multiply this one by ky squared. That is the second moment of area. Hence, your radius of gyration with respect to the y-axis is now equal to the square root of the moment of inertia with respect to the y-axis all over the total area. Okay, let us try to determine the moment of inertia of this rectangular figure shown. The base is B and the height is h. So we have your moment of inertia by integration. Now, let us try to consider a differential strip of this total area. So we now have, this is now the differential strip that we are going to consider, such that the height of this differential strip is equal to, now the distance of this differential strip, okay, to the x-axis is equal to y. So this is equal to y. And therefore, the height of this differential strip taken is d sub or dy. So from the definition of moment of inertia, or this is the second moment of the area, the moment of inertia of this differential strip considered about with respect to the x-axis is now equal to the integral. So we have the y square multiply this one by the a, or your ix in here is now equal to the integral of y square multiply this one by the a. And the area of this differential strip considered is b multiply this one by dy. That is b multiply this one by dy. So that is from 0 to h. So that is 0 to h. Or your ix is now equal to, let's bring out b outside the integral sign. So this is now b, the integral from 0 to h. That is now y square dy. So y square multiply this one by dy. So that the moment of inertia with respect to the given x-axis, or this is at the base, at the base of the rectangular area. So this is therefore equal to b, the integral of y squared dy is equal to y cubed all over 3, that is from 0 to h. So your ix is therefore equal to, let us try to substitute upper limit minus the lower limit. So your lower limit in here is equal to 0. So this is therefore equal to b h cubed all over 3. So that is the moment of inertia of this rectangular area with respect to the x-axis. Now, let's try to determine now the moment of inertia with respect to the centroidal axis of this. So we have the moment of inertia with respect to the centroid. Okay, so let's consider now that the centroid of this rectangular area is located at this point. So that is now the centroid. Now, such that the centroid of this area is h all over 2 from the x-axis. So this is h all over 2 from the x-axis. So that is now your h all over 2. Now, using the parallel axis theorem, so let's try to using the parallel axis theorem, or transfer formula for moment of inertia. So that is for moment of inertia, then so we now have this axis in here is now your x of O. So I'm going to consider this one as x of O. So that is the axis. So we now have the axis corresponding to the centroid of the rectangular area. So from the parallel axis theorem or transfer formula for moment of inertia, the moment of inertia about or with respect to an axis, to any axis x, is now equal to the moment of inertia with respect to the centroid of that body. That is now IXO plus AD, that is now y squared. So we get the distance which is parallel to the y-axis. Now, your IXO, if you try to recall your parallel axis theorem, okay, the axis corresponding to the centroid of the area considered is x prime. At this time, I'm going to consider this axis as x of O. Now, so your area in here is now equal to, so your area is equal to B, multiply this one by H, and your distance D parallel to the y-axis is now equal to H all over 2. So that is H all over 2. Now, the moment of inertia about this axis, about the x-axis, is BH cubed all over 3. So this is now BH cubed all over 3 is now equal to the moment of inertia with respect to the centroid of the area in the x-axis plus ADY squared. So here A is B, multiply this one by H, multiply this one by D, Y is H all over 2. So we have your IXO is now equal to, we have your B H cubed all over 3, transpose that is BH cubed all over 4. BH cubed, H times H squared, H cubed, 2 square is 4. So this is equal to, so we have, that is 12. So we have 4 BH cubed minus 3 BH cubed. Hence, the moment of inertia with respect to the centroid of this rectangular area in the direction of the x-axis, IXO is equal to BH cubed all over 12. That is equal to BH cubed all over 12. Now, I'm just going to have one illustration for moment of inertia by integration, because you have taken this one, or you will be taking this one in your calculus, moment integral calculus. Now, the table that was uploaded shows the moment of inertia of a common or spatial geometric figures. Again, when we say common or spatial geometric figures, we have your rectangle, we have your triangle, your circle, quarter of a circle, and so forth. Okay, so, but you try to take note with the orientation of the axis. Okay, the orientation of the axis in your table. So, the x-axis, the y-axis, your xo, and your yo are indicated in the table uploaded before. And those values in the table were all derived using moment of inertia by integration, because we will be using this one as we proceed to moment of inertia of composite figures. Okay, so in this figure, let's try to determine the polar moment of inertia and the polar radius of gyration of the shaded area shown with respect to point P. So first, let us try to divide this composite area. So I'm going to get, the first one in here is I will going to get the whole area. So if I will going to get now the whole area, so this is now the whole area. Now, such that this is now the area. So we have for A, so this distance in here is A. So we have for A, and this distance in here is 2A. So this is your axis, y-axis. And this is the x-axis. X, and that one is now the y-axis. And then we have to remove this area in here. So that area, so we have the second area. So I'm going to remove the first or the second area. So this is having 2A and A. So this is your 2A, and this one in here is now your A. So we have to remove this one in here. So we have to subtract. So this is now 2A, and this is now having a distance A. Again, this is the y-axis, and this one in here is the x-axis. X, y, this is your point P, and that is now your point P. So we have the first area, and this one in here is now the second area. Now, such that the moment of inertia for the first area, so we have your area 1. Okay, so for the first area, let's try to get now the moment of inertia with respect to the x-axis. So the moment of inertia with respect to the x-axis, so let's start with area 1. So we have your area 1. So this is now your area 1. So we have your Ix1 is now equal to, this is a rectangular area, that is BH cubed. Now this is at the base of this rectangular area, so that is BH cubed all over 3. You try to go over the table that was uploaded. Table of moment of inertia of spatial or common geometric shapes or geometric figures. So that your Ix1 is now equal to B is equal to 4A. That is 4A. Your H in here is equal to 2A. So that is 2A cube. Okay, so that is 2A. So this is cube all over 3. So your Ix1 is now equal to 4. So your Ix1 is now equal to 2 cube is 8 times 4 is 32. So we have 32, 8 to the 4th all over 3. That is 32 a to the fourth all over 3. Then we have your ix2 for the second area. So your ix2, again, the x-axis lies or coincide with the base of this area. Hence, again, this is bh cubed all over 3. So we have your ix2, your b in here is 2a, and then we now have your a cubed all over 3. Hence, this is therefore equal to 2a raised to the fourth. So your ix2 is equal to 2a raised to the fourth all over 3. Now, your ix is now equal to ix1 minus ix2 because we have to remove this one. We did consider the whole area in here. So we have to remove that area. So that is the moment of inertia with respect to the x-axis. So your ix is now equal to 32a raised to the fourth all over 3 minus 2a raised to the fourth all over 3. We now have your ix is equal to 30a to the fourth all over 3, or this is equal to 10a to the fourth. So it's the moment of inertia with respect to the x-axis. Now, let's proceed now with respect to the y-axis. So this is with respect to the y-axis. So that is with respect to the y-axis. So for area 1, your iy1 is now equal to. Now, you try to take note in here now that the y-axis passes through the centroid of this area. So let us try to get now the centroidal moment or the moment of inertia of this area with respect to the y-axis. And this is therefore equal to bh cubed all over 12. So we have your iy1 is now equal to b, which is equal to 4a, multiply this one by 2a, Okay, so your b in here, you try to take note that with respect to the x-axis, now if you have a rectangular area, or if you have a triangular area, the base is always, you get the base parallel to the axis where you take moment of inertia. And the base for iy with respect to the y-axis, your b in here is the axis parallel to the y-axis, and that is equal to 2a. So that is now equal to b is 2a, multiply this one by 4a cubed. Multiply this one by 4a, that is cube all over 12. So your iy1 is now equal to, iy1 is now equal to 4 cubed by 2 is 128. That is 128 a raised to the fourth all over 12. For area 2, we have your iy2. Again, the y-axis in here passes through the centroid of this area. So we have to use the centroidal formula for moment of inertia with respect to the y-axis. Again, this is b h cubed all over 12. Again, your b in here is the base or parallel to the y-axis. So that is equal to a. So that is a, and then your h in here is 2a. And this is square. So 2a cubed all over 12. So we have the moment of inertia with respect to the y-axis of area 2. 2 cubed is 8. So we have 8a raised to the fourth all over 12. Now, the moment of inertia, therefore, with respect to the y-axis is iy1 minus iy2. Again, we remove the area. So your iy is now equal to 128. That is now your a raised to the fourth all over 12 minus 8a raised to the fourth all over 12, or this one is equal to 120 a raised to the fourth all over 12. So, the moment of inertia with respect to the given or y-axis is now equal to 10a raised to the fourth. Now, the polar moment of inertia so that is now the polar moment of inertia. The moment of inertia at point P, so that is equal to Ix plus Iy. So the polar moment of inertia is now equal to 10a raised to the fourth plus 10a raised to the fourth. So we have 20a raised to the fourth. And the polar radius of gyration. So we now have the polar radius of gyration. Okay, so the polar radius of gyration, so that is now KO, is now equal to the square root of the polar moment of inertia all over the total area. So the total area is area 1 minus area 2. So we have the total area is equal to, so I have your 4a, the first figure, 4a multiply this one by 2a minus 2a multiply this one by a, or this is equal to 6a squared. So the polar radius of gyration is now equal to the square root of 20a to the fourth all over 6a squared. So this is therefore equal to 1.826a. A to the fourth over a square is a square. Square root of a square is a. And the square root of 20 over 6 is 1.826. So that is the polar moment, polar radius of gyration. Next, determine the moment of inertia of the beam cross-section about the centroidal x and y axis. So this is a symmetrical beam. There's 50, there's 150, 50, 150. So we have, this is, 50 and 450. So, of course, the centroid of this lies at this point in here. So, with respect to the centroidal x and y axis. So, this is therefore the y-axis, and we now have your x-axis, which this is now x-axis, and this one is the y-axis. So I'm going to divide this into three areas. First is this area in here. Now, such that this is now area 1. So we have your area 1. So this is your area 1. So this is now the centroid is located at the x and y axis indicated in the figure. So we have the y axis, and this one in here is now the x axis. Now, this is 200, 250, so we have 450 millimeter. And this one in here is equal to 50 millimeter. So that is 450 millimeter. Now, so for area 1, the moment of inertia. So for area 1, the moment of inertia with respect to the x-axis. So your Ix1 is now equal to, now since x and y axis passes through the centroid of this area, so your Ix1 is bh cubed all over 12. So we now have your Ix1, so your b is 50. So we have 50, your h is 450 cubed all over 12. So that is now your Ix1. And this one is now equal to 379. So this is equal, so Ix1 is equal to 379.6875. 6875 times 10 to the 6 millimeter raised to the 4th. Okay, millimeter to the 4th. And then we now have your, so the moment of inertia with respect to x and y axis. So your Iy1 is now equal to, again, this is passing through the centroid. So we still have your Iy1 is still equal to bh cubed all over 12. bh cubed all over 12. And your b by this time is now 450. That is 450. Your h is 50 cubed all over 12. So we now have your Iy1 is now equal to 4 points. That is 4.6875 times 10 to the 6 millimeter to the 4th. Let's proceed now to the second area. So I'm going to consider this one in here as the second area. So this is now the second area. So for the second area, this one is 50 mm and this one is 150 millimeter. Now, so the y-axis is at this point. So this is therefore the y-axis. And this one in here is now the x-axis. Okay, so the x-axis. So this is now the centroid. The x-axis lies or passes through the centroid of this area. Now, such that this distance in here is now equal to 25. So that one is equal to 25 millimeter. That is equal to 25 millimeter. Now, the moment of inertia with respect to the x-axis, which is now your ix2 is equal to bh cubed all over 12 because the x-axis passes through the centroid of this area. Hence, this is now your b is 150. That is 150 multiply this one by 50 cube all over 12. So we have your ix2 is now equal to 1.5625. 5625 times 10 to the 6 millimeter raised to the 4. And then we now have your IY2. So your IY2 is now equal to, so this is now this point. So the moment of inertia with respect to the y-axis. Now you try to take note that the moment of inertia is no longer passing the base or the centroid of this area. So we will now make use of the parallel axis theorem or the transfer formula for moment of inertia. So the moment of inertia with respect to the centroid of this area is bh cubed. So that is IXO plus. So we have the moment of inertia with respect to the centroid of this area plus A multiply this by B parallel to the x-axis square. And the moment of inertia, IXO, with respect to the centroid of this area. So if this is now your X of O, and that is equal to BH cubed all over 12. So that is BH cubed over 12. Your B in here is 50. That is 50 BH. Your H is 150 cube all over 12 plus the area which is 50 by 150. So the area is 50 multiply this one by 150. That is your A. And your dx is now this distance. So your dx is this distance. So this is the distance from the centroid of this area to the y-axis. And that is now your dx. Now, such that this distance in here is equal to, so that this one in here up to this point is equal to 150 is 75 millimeter. Hence, the value of your dx is 75 plus 25, or that is equal to 100 millimeter. So multiply this one by d square, and that is equal to 100 square. So we have your IY2 is now equal to 89.0625. 0625 times 10 to the 6 millimeter raised to the 4th. And then we have your area 3. So this is now your area 3. Okay, so we have your area 3. So that is 150 millimeter, and that one is 50 millimeter. So again, this is now the location of the y-axis. So this is now your y-axis. We have the y-axis, and again, the x-axis passes through the centroid of this area. Okay, so that is now the location of the x-axis. Okay, again, your IX3, your IX3 is equal to BH cubed all over 12. Okay, so that is the moment of inertia with respect to the centroid of this figure in the x direction. So we have your IX3 is now equal to B is 150, H is 50 cubed all over 12. So your IX3 is equal to 1.5625 times 10 to the 6 millimeter raised to the 4th. Again, your IY3. Okay, so that is for area 3. Again, your y-axis. Your y-axis doesn't coincide with the base, nor passes through the centroid of this body. So we'll try to make use again of your transfer formula for moment of inertia. So we now have, so this is now your, the centroid. I'm going to call this one in here as the centroid, your YO. Now such that this is now the distance x. So we have your, so this is now your, okay, so that is your the distance from the y-axis to the centroid of this figure. Again, this distance in here is 25 millimeter. And this distance up to that is 75 millimeter. So 25 plus 75, so your dx is 100 millimeter. Again, IY3 is now equal to the moment of inertia about the centroid of this figure plus a dx in the direction x square. So this is IY3 is now equal to BH cubed over 12 plus a dx square. So we have your IY3 is now equal to B. Now, your B is now the distance or the dimension in the direction of the y-axis again. So that one is 50. Your h is 150 cubed all over 12. Plus, the area again is 150 by 50. Your D is 100 square. So your IY3 is equal to, so we have 89.0625 times 10 to the 6 millimeter raised to the 4. So let us try to determine now the moment of inertia. So your moment of inertia about the centroid of the whole body or of the whole figure is now equal to Ix1 plus Ix2 plus Ix3. And this is equal to Ix1, 379.6875 times 10 to the 6 plus 1.5625 times 10 to the 6 plus 1.5625 times 10 to the 6. So that is equal to 382 point. So we have 382.8125. 8125 times 10 to the 6 millimeter raised to the 4th. And the moment of inertia about the indicated y-axis is Iy1 plus Iy2 plus Iy3. And this is equal to, so Iy1 is 4.6875 times 10 to the 6 plus Iy2, 89.0625 times 10 to the 6 plus Iy3, 89.0625 times 10 to the 6. Or this one is now equal to 182. So that is 182.8125. 8125 times 10 to the 6 millimeter raised to the 4th. Okay, next. Let's try to determine the moment of inertia with respect to the y-axis or about the y-axis. Now, again, I'm going to divide this composite area into special geometric areas. So first, I'm going to consider this as now the area. So we have the first area is your triangular area. The second area is your square area, 150 by 150. And we have the third area, we have your rectangular area, 150 by 300 millimeter. Okay. Now, so for the first area, so this is the first area. This one is 50 millimeter, 150 millimeter, and this one is 150 millimeter. So we have about the y-axis. So this is now the y-axis. So the moment of inertia of this area about the y-axis is now equal to dh cubed. For a rectangular area, the moment of inertia with respect to the base of this triangular area, so that is Iy1, is now equal to bh cubed all over 12. So that is with respect to the base of this triangular area. So that the moment of inertia is now equal to, again, your B in here is the dimension parallel to the axis where moment of inertia is required. So that is equal to 150. This is your 150. So it just so happened that this is also 150. So we have 45-degree triangle. So we have 150 cube. Itong 150 na to is to. So that is the dimension parallel to the axis where moment of inertia is required. And this is now your 150 cube all over 12. So that the moment of inertia is now equal to, so we have 42.1875. 42.1875 times 10 to the 6 millimeter raised to the 4th. Now, I will going to get now the second area. So, this is now the second area. So again, we have 150 mm. And this one is 150 mm. Now, we have the x-axis as another y-axis. So we are required to determine the moment of inertia with about the y-axis. This is now the y-axis. So, the moment of inertia of the second area about the y-axis is now equal to, again, we have a rectangular area. So that is BH cubed all over. Now, since the y-axis in here passes through the base of this rectangular area, so that is BH cubed all over 3. So your IY2 is now equal to, again, your B in here is the dimension parallel to the y-axis. And this is 150. So we have 150, multiply this one by h cubed. So your h is this one, 150 cubed all over 3. So we have your y2 is now equal to 168.75. 168.75 times 10 to the 6 millimeter raised to the 4th. And we now have the last area. So this is the last area, which is area 3. So we now have your area 3. That is now your area 3. So, we have 150 mm, and this is equal to 300 millimeter. Now, again, the y-axis is this is now the y-axis. So again, the y-axis is along the base of this rectangular area, Hence, the moment of inertia of the third area with respect to the y-axis is now equal to bh cubed all over 3. That is bh cubed all over 3. Iy3 is now equal to b. Again, your b is the dimension parallel to the y-axis. Because we are getting moment of inertia about the y-axis, hence, your b in there is 300. Your h is 150 cubed all over 3. We have your y3 is now equal to 337.5. 337.5 times 10 to the 6 millimeter raised to the 4th. And the total, the moment of inertia about the y-axis is equal to iy1 plus iy2 plus iy3. So the moment of inertia is now equal to 168.75 times 10 to the minus 42.1875 times 10 to the 6 plus iy2 168.75 times 10 to the 6 plus iy3 337.5 times 10 to the 6, or this is equal to 548. So we have 548.4375. 4375 times 10 to the 6 millimeter to the 4th.